Hi everybody, welcome to the next session on Multimediale Werkzeuge. Today about the inversion of the DCT and the separability for two-dimensional signals. So here again is the equation that we have for the discrete cosine transform. So x is our input signal, for instance a row of our image. And here these might be luminance samples or also chrominance, which means the color components. And then we have the DCT going over a block length of capital N samples. So often in compression this is just 8 samples long. So then we would have a sum going from 0 to 7. Takes 7 luminance values, and each is multiplied by this cosine term here, and this cosine term again contains this index n. So this would be the location index, and then we have this index k, which is the subband index or the spatial frequency index, and this also runs from 0 to capital N minus 1. Yeah, so this means we have n equations for each subband 1, and also n sums. And furthermore, we have exactly n input values. So for each n from 0 to n minus 1, a value of the output is obtained. So there should be a comma. So we have n input values and n output values, and between them is a linear transform. Right. So we have a system of equations with n variables, like this. So we rewrite the summation here simply as matrix multiplication. So when we have this column vector for x, so this contains, for instance, our 8 luminance samples along a row of our image, and then we multiply this column vector with the first row of this matrix, and we get the sum for k equals 0. Right? So as the output we get y of 0, so k is equal to 0. For the next row we have the cosine terms for k equal 1, so here you can see a 1, and we get the result for k equal 1 as y of 1, and so on until we get y of n minus 1. So here we can see in this way we have a matrix, the matrix T, which has n rows and n columns. So it's an n by n matrix, and hence it's invertible, which is important for the decoding side. When we use this transform in an encoder, then the encoder gets the frequency coefficients, the DCT coefficients transmitted, and then the decoder needs to invert it. And we can do that by simply multiplying with this inverse matrix T. And we can compute this inverse because it's a square matrix. So if x is unknown and y is known, as in the decoder, the equation can be solved by simply using matrix inversion. So here we can see it. We have our t times x, and if you multiply it by the inverse of t, then we get x. And that's basically what we do in the decoder. We multiply y with the inverse of t. So this is how we solve it for y. As I mentioned, this is used by the decoder to return from the local frequency range to the I should call this domain. So we come from the frequency domain to the spatial domain, back to the spatial domain. Spatial domain. And that means the original image basically. So here in summary, we have the encoder, which computes our DCT coefficients, y, the frequency coefficients. So then we have a time or space frequency. So this is actually, in this case, space. And On the way back, we also get back to space. So it depends on which domain you apply this DCT. It could be a time signal, but in our case here it's a piece of an image. We have either frequency in the time domain or in the space domain. Yeah, so the advantage of the matrix representation is that it tells us how to return to the spatial domain. And thus giving us the inverse transform, which is important in the coder context. So basically now we have it. We have the piece for the encoder and for the decoder. What's still missing is the extension to 2 dimensions. So what we have is representation for vectors, which are 1-dimensional signals, but in images we have, for instance, those 8x8 pixel blocks like in JPEG. Right, so these are pixel blocks. And the goal or the objective is the application of the DCT to the 8x8 image blocks. So 2-dimensional. So here maybe we say 2-dimensional 8x8 image blocks. So the approach is to divide the blocks into individual rows, and each row is 1-dimensional again. This means that we can now apply the DCT matrix T to the rows, which means multiplying it from the right hand side. Right? We do this with each of the 8 rows. So the result is an 8x8 image with spectral values of the DCT in each row. And the next step would be accordingly for the columns. So starting from this last 8x8 image with the spectral values in its rows, we now apply the DCT to the columns. Right, so we take each of the resulting columns and apply the DCT to them. And the result is then an 8x8 image with spectral values in the rows as well as in the columns. Right. And we also saw the order of the application to rows or columns does not matter, since we can swap the sums in the original formulation of the 2D DCT. 2D DCT. Right. It doesn't matter in which order we place the sums. Yeah, so we have a linear transform. So this is the multiplication with the T. It's a linear transform. And that results in a so-called separable 2-dimensional transform. Separable, which means we can separately apply it to rows and columns. So why is actually the second step to the columns necessary? Because in step 1 we get the spectral components over the rows alone. That means we get the spectral frequencies corresponding to the signal along the row. So if there's fluctuations along the row. Vertically, however, the original brightness curve is still present in the intensity of the horizontal spectral components. Right? For instance, if we have vertical stripes, then horizontally they change the brightness, but vertically they don't. So vertically we would only have frequency 0, but the high frequencies would disappear. And we can take advantage of this property only if we also apply the DCT vertically. Yeah, so this means to obtain vertical spatial frequencies or spectral components along the columns, we also need to apply the DCT along the columns, which means a multiplication of the column vectors by T transpose. So here's an example. This is the original image. So this is Ilmenau in November. A nice snowy image, which has the advantage that we have a big contrast between white and dark brightness here. Or like here, sharp edges at the rims of the window here. So good test image. So then I took the monochrome image, which means the Y component, split it into 8x8 pixel blocks, and then apply the 2D DCT to each pixel block. Right, so this is actually the 2D DCT. And we see that the bright spots mean large DCT spectral values, yk. So now in each block we have the coefficients of the DCT, yk. So actually here it's y, it's two-dimensional, so it should be having another index, say L. So we get 8 by 8 spectral values, and large values, large magnitudes are represented here in this image as bright luminance, so bright spots. So here you can see, like in the tree, you have more bright spots, and that's because they have more high frequencies. Right? When you look at the original, there are fine details here, and then these fine details means we have high spatial frequencies. So the corresponding pixels here become bright, and that's why the trees appear bright here. And then we have smooth surfaces like the snowy region here, and these snowy regions and also the sky here appear dark because only y of 0, 0 is high, means bright. So only one pixel in each of those 8 by 8 blocks appears bright, and all the rest of the 63 pixels is dark. And that's why the sky and the snow areas appear dark here in this DCT transformed image. Yeah, so here you can see how you can generate it in Python. So in Python, to apply the DCT to blocks of 8 by 8 pixels, you could use 2 for loops to go over each of those blocks. But then it turns out that it's quite slow to use 2 for loops, a nested pair of 2 for loops in Python. It's much better to use matrix operations. And this is what I did here with the help of the reshape command. So first here I turn the image into the Y component. So here you can see the factors which come from the color transform for the Y component. And then here I'm extracting the shape of our image. So like 480 times 640. And here I'm applying now this reshape. So I'm taking this luminance image and reshape it such that it consists of 8 columns. So each row is only 8 pixels long. And the -1 means take as many rows as needed to accommodate all pixels. And order C means it first goes along the columns. So it goes along the rows. So first it takes the first piece of the first row, and after 8 pixels are over, then it puts the next 8 pixels in the next row, and so on. And this division by 255 is just a normalization to get the values into a float range from 0 to 1. Remember, when the image comes from file, here this JPEG file, then it is represented as 8-bit integers, right? So that means we have a value range from 0 to 255. But since it's float, we prefer to have it in the range between 0 and 1. So this is what I'm doing by division by 255. Right. Okay, so after we did this reshaping, we apply the DCT to this tall image. So remember, this image is only 8 pixels wide, but many pixels high. So here the DCT is applied to axis 1, meaning along the rows. So now in this step, each row is DCT transformed. So that's good, right? And then we shape it back. So after each snippet of all the rows is transformed, we shape it back to the original size. And now we want to apply the DCT to the columns. And instead of applying the DCT to the columns, we transpose the image. And this has the advantage that we just copy and paste the commands that we just saw. Right, so here I have the transposed image, do the same reshape, DCT again along the rows, because in the transpose the rows are the columns of the original, and then we shape it back. And now in this capital X we have the rows as well as columns of each 8x8 pixel block transformed. So now we can also take a look at it with ImShow. This shows us the two-dimensional DCT, and we can also look at ImShow using the logarithm, which has the advantage that we see small values better. So let's see if we can actually do it here. So let me open a terminal window. Open terminal. So here's now my terminal. Let me make it a little bigger. And then try to do this. Right, we start with IPython PyLab. So I copy it and paste it. Oops. Okay, that's better. Oh, interesting. Oh yeah, it was the wrong minus sign here. That's sometimes happening from copying from a document to the terminal. Okay, so now I'm using FFTPack. So here importing FFTPack, which contains the DCT. So next I'm doing the imread and imshow. Let's see if that works. Yes, so here you can see the picture, right? This Ilmenau picture, that works. So then we can turn it into a luminance picture. Copy, paste. So we can also say imshow of y. So now we have the black and white image. It just appears colorful because now the different brightness is displayed with different colors. Right, so this makes it easier to distinguish different brightness shades. Yeah, and then we can do our reshaping trick. Let me see here, when we use CMap equal gray, then we can actually have it in a more natural representation. So here, comma, paste CMap gray. Yeah, so now you can see it here in the natural gray level scale. So this is then the Y image that we now want to transform. Okay, so let's do the transform now. So here we do the reshape and applying the DCT. So paste. So now we have the X, and now we have to do the same with the columns. So reshaping back and applying the DCT to the columns here. Paste. Now it's done. Great. So now we can actually take a look at the resulting image, the grayscale image. So here you can see that it's not really black. We have it in gray shades, and this is because the higher frequencies above frequency 0 also can have negative values, and they're usually centered around 0. So that's why 0 here is displayed as a gray value. So that's not so useful. So that's why it's more useful to display the magnitude. So let me try the apps of X. So here you can see that now has 0 as black. And still we don't see that much because the small values basically disappear, and that's why we try the im show to the log. Copy, paste. So let's see how this is doing. Yeah, so this is actually now looking better because now we can also see the smaller spectral values more easily, right? Before it was dominated by the DC values, which are by far the highest, which you can see here, right? You can still see it. The DC values are really high, and if you don't apply the log, then the other values from the higher frequencies are so much lower that you don't really see them with the eye. That's the problem, and that's why it's useful to apply the DCT apply the logarithm to the values, to the magnitude of the values. So now I can also zoom in here. Let's take a piece here. So yeah, this looks nice, huh? So here you can see this is branches of the tree, and here you can see each of those 8x8 blocks, right, in the DCT domain. So each 8x8 block now contains the coefficients of our DCT, and you can see here in the upper left hand corner those bright spots here are the DC coefficients. So they are always very high, and this is typical for natural images, that the DC values, the y of 0, 0 is by far the largest, and that's why they appear the brightest. And when you come into the branches of the tree, you can also see that the other coefficients now become larger, and this because of all the detail that those branches, those pine trees have, right? They have many high frequencies, and this is what you can now see here. I could even go in more inside. Maybe that's too much. So try it again. Zoom into those branches. Again. So zoom to those branches, and you can see it. So again here, 8x8 pixel blocks. Here you can see DC, y of 0, 0. Here are the higher spatial frequencies, and here they are clearly visible, but outside the branches there's not so much, right? Here you have DC clearly the highest, but then the other coefficients are fairly small. But here in the tree they become also significant because there's more fine detail here. Yeah, this also shows here the advantage of doing the example here on your own in the terminal, because then you can zoom into the plots and get all the details which you cannot really see when you just download the picture and look at it. Yeah, so it's always worthwhile to do it on your own. So yeah, we still see that the biggest part of the picture is basically black, or let's say small values. You have many very small values, and that's good for coding, right? And also when you do quantization, small values are often quantized to 0, and then you have many zeros in a row, right? And then we can apply run length coding. And this is used, for instance, in JPEG for high spatial frequencies, as they're usually very low and quantized to zeros, and that means we have many consecutive zeros. Yeah, this is particular when we have uniform areas. We have high spectral values at low spatial frequencies, the DC component, let's say 0 for 2 dimensions, and that means we have small values at high frequencies, at high spatial frequencies, as we just saw in the areas of the snow and the sky, for instance. Yeah, and now we can also take a look at how the different resulting subbands or images of the different spatial frequencies look like. So for this, we can combine the same spatial frequencies of all small 8x8 blocks into a new image. For instance, we take all the DC coefficients, collect them from all blocks, and put them into a new image. Right, so for k equals 0, L equals 0, so then we have all DC coefficients, collect them together, and put them into a new image. Yeah, so in Python we can do it with this code here. So we have our X subband image, which we initialize with the same shape as our original image, and then we just collect the corresponding coefficients. So here we have two for loops. So here those for loops are okay because it's just ones, and here we have it fairly short, so it's just 8 by 8 loop length. And here we look at the corresponding subband coefficient for each block. So here we have the coefficient kV, which is the block index vertically, V for vertically, and we have kh, this is the block index horizontally. So this is what we have here, right, this kh. So here you can see this kV is the index of the blocks horizontally, right? It goes from 0 to 8, and it basically divides the rows of the image into 8 pieces. So here we have then the index 1/8 of the row size, right? And here we have this basically runs it's taking 1/8 of the row of the rows. So this is then the first part horizontally, and this is the corresponding 1/8 vertically. So this is a resulting subband image, and this subband image, which has 1/8 of the width and 1/8 of the height, now gets assigned the corresponding coefficients of our DCT transformed image. So here we see it. We start with an offset of kV horizontally, or vertically and horizontally, and we increase our index by 8. So if we start here with 0, 0, then it jumps 8 horizontally and vertically. So here it jumps 8 vertically, and here it jumps 8 horizontally. So for kV and kh equals 0, this collects all DC coefficients into this subband image. And corresponding for the other coefficients. So if we start here by with 1, then we have index 1, frequency index 1 vertically, and still 0 horizontally, and so on. So in this way, each of those subband images gets a specific frequency, spatial frequency, horizontally and vertically. Yeah, so we can actually also try it in IPython. So here I'm using the initialization first, copy, paste. So now we have the initialization. Now here I have the two for loops, copy, paste. So now I need to fill the for loop with this here. It has a line break in it, which I have to remove. So hopefully it works. Yeah, this seems to work. Okay, so now I can use imshow to copy to show it. V. So here you can see the result. It looks kind of interesting. You can see in the upper left hand corner you see the DC coefficients. And the collected DC coefficients, they just look like a tiny original image. And that makes sense because when you think about it, the DC coefficient was just the brightness average over an 8 by 8 block. And if you just take one pixel from each 8 by 8 block and each representing the average, then this is basically the downsampled image. The rest looks kind of different. So here when you look at the neighboring images, like these here, Right? You see here in this case, it looks like you only have the vertical edges. So here you see the vertical edges emphasized, and also the vertical edges in the trees here. And remember, here I have not the magnitude, but here I also have the high frequencies with negative values in it, so that 0 means gray here. But that actually accentuates the edges. So one side of the edge is really dark and the other side of the edge is brighter because it has negative values. So that makes it actually easier to see here in this case. So it also gives the image kind of a plasticity. So it seems like this is really like shadows and light. So it's kind of interesting. So this is to the right. So now we have 0,1. This corresponds to frequency 0 vertically and 1 horizontally. There we have those vertical edges. Right. So this extracts vertical edges. And if I go to the one below, like this one here, again, so this image here, you can see this is basically doing the same thing, but vertically, horizontally. So you can see here the horizontal edges are emphasized or filtered out. So this only contains the horizontal edges. Also the same for the tree, and here parts for the roof. So you can see that those filters, they filter out edges of a certain orientation. Right? So it's kind of an interesting property that they have. Now I can also take a look at the first diagonal image. And here you can see this basically filters out diagonal images. As you can see here. No horizontal edges, no vertical edges, but only diagonal edges, which in this case only appear in the trees. Right? And that's why you only see the trees, because only they contain diagonal edges. So these are edges on one diagonal and also on the other diagonal, on both diagonals here. So in that case, it's not as discriminative as the horizontal and vertical. Here you actually have two orthogonal edges, both diagonals. Right. So yeah, then you can see here the higher frequencies mostly disappear. Right? When we zoom in here, there's hardly anything to see. Right? It's basically all 0, and that's what's happening here. So this allows us to perform good compression, because there's basically just zeros in the biggest part of the DCT transformed image. So here you can effectively apply run length coding, particularly if you just look at this lower triangle here. And that's why in JPEG, for instance, the order of those coefficients is taken along a zigzag scan. So they have a zigzag scan, and you can see after a certain time the zigzag only covers zeros, and then you can very efficiently apply run length coding. Okay. Yeah, so this is basically what we just saw. So here we have the DC coefficients. Here are the coefficients for L equals 0 and K equals 1 up to K equals 3. Then here we have the coefficients for K equals 0 and L equals 1, and going down to L equals 3. Yeah. So question, what does an image look like in which all vertical edges, i.e. their higher spatial frequencies, are set to 0? So we take this DCT image, basically just zero out all the high frequencies and then apply the inverse DCT. Right? Yeah. And then inverse DCT transformed. Yeah, the answer is we lose the sharp edges, right? So the sharpness is gone. So the edges appear blurred in the reconstructed image. That means we have 8 by 8 blocks with a gradient over each block. Let's say each block. Okay, and these experiments I will continue in the next set of slides. So thank you for your attention and see you then in the next part.